Alright guys, so real quick, I'm not going to go through everything of 6.1. Did want to point out some of the key stuff for it though before we start in 6.2 to talk about what are called Hamilton paths and Hamilton circuits. So first, let's just make sure we understand the idea behind a traveling salesman problem. So traveling salesman problems are similar to the types of problems we were working before, where we had paths, we had circuits, we also had these edges and these vertices. The big difference, though, is that now in a traveling salesman problem, each of the edges is going to have some kind of a number attached to it, which we're going to call the weight for that edge. So all of our graphs for our traveling salesman type problems are going to be what are called weighted graphs, meaning that each one has a different value. And for example here, you've got a person or a salesman getting ready to travel between some different cities. Obviously, you want to try to find the cheapest route between all 5 of those cities. So you're looking for what is the cheapest possible way to get from one to the next. Another example that's kind of cool to think about is looking at the outer moons. So looking at the moons for the planets and trying to travel to those. Obviously now, rather than looking at the cost in terms of money, we're looking at a cost in terms of time, and that we're looking for what is the shortest amount of time that we could possibly use in order to visit these different moons. Kind of cool stuff when you think about it. So really what I wanted to make sure that you guys understood about these problems, in each of those cases, each of those problems that we are looking at, we're looking for a tour. In other words, we're looking for a trip that starts at one point, ends at another point, and visits each of the different sites once. So rather than looking at going through each path once, we're only looking to go to each vertex once. Now, we also have this idea of an optimal route where we're looking for what is the least total cost, be it money, be it time, all those sorts of things can represent cost. When we talk about these types of situations, we more commonly refer to them as a traveling salesman problem or a TSP. Now, most of the time we're not actually talking about a salesman that's traveling, but we could. So obviously there's a couple of examples that you can read through to see where these are used in the real world. Obviously, we are going to be looking more at the math behind it, and we're going to do that by looking at what are called Hamilton circuits and Hamilton paths. So I'll let you read through those examples. Don't want to talk too much about 6.1. I'd rather focus our attention on 6.2. So in 6.2, the main idea of this section is to talk about what are called Hamilton paths and Hamilton circuits. Obviously, in Chapter 5, we just got done talking about what are called Euler Paths and circuits. These were the names that we were given when we found either a path or a circuit that included every edge of the graph, and only once. Remember, no repeats if possible. We're now going to discuss something that's somewhat similar. We're still going to be looking for paths and circuits, but now we're only interested in making sure that we include each vertex of the graph once and only once. So we're going to shift our kind of point of view and our goal from going through every edge to going through every vertex. And it's going to be a big change. You would think that it was not such a big difference, but it really is. So let's define what is a Hamilton path versus what is a Hamilton circuit. So a Hamilton path is a path that includes each vertex of the graph once and only once. Whereas a Hamilton circuit is a circuit that includes each vertex of the graph once and only once. So obviously at the end, the circuit has to return to the starting vertex. You have to kind of finish that loop in order for it to be a circuit. So yeah, on the surface level, the only difference is we're shifting from looking at edges to looking at all the vertices. But it's going to be a huge difference when we get into it. So, looking at this figure, and we've seen this figure before when we were talking about Euler circuits and paths. Remember that this graph actually had an Euler circuit, and we were able to figure that out by noticing that each of the vertices had an even degree. But we also now are going to look at it in terms of a Hamilton circuit. So with a Hamilton circuit, you want to start at one vertex and end at the other, or end it at that same vertex, going through each of the other vertices once. So the example that they suggested is from A going to F, then to B, then to C, then to G, then to D, then to E, and then back to A. And so notice that while that actually does go from A back to A, and it does go through every vertex, that definitely is technically a Hamilton circuit. But it's definitely not an Euler circuit. Remember, for an Euler circuit, we would have also needed to use a few of these other edges as well, and we didn't. So actually, it's a little bit easier, if you think about it, to find a Hamilton circuit than it would be to find an Euler circuit. Now, obviously, if a graph has a Hamilton circuit, then it makes sense that it automatically has a Hamilton path. Remember, the only difference between the two is that a circuit has to be ended at the same vertex that you started. For example, if we were to go back and look at our graph, if we wanted to change this from being a circuit to a path, all we would have to do is get rid of that last step. And now, instead of ending at A, we end at E, but we've still gone through each of our vertices just once without ending back where we started. So every circuit has a path. That's not necessarily true the other way around. It does not necessarily mean that paths also have circuits. All right. So as another example, let's talk about the difference between Hamilton versus Euler. Obviously, we saw in a previous section that this graph has no Euler circuits, but it does have Euler paths. However, this graph also has no Hamilton circuits because sooner or later, once you go to C, you're stuck there. So if you start at C, there's no way to get back to C. And if you don't start at C, then eventually you have to go to C, and there's no way to get back to where you started from. It does, though, have Hamilton paths. So obviously that's pretty easy to do. Just start anywhere you'd like, maybe A, go to B, to E, to D, to C, and so on. So some more examples of this. The graph that we're looking at here has no Euler circuits, no Euler paths, because it has 4 odd vertices on the corners, so no paths and no circuits. But it does have Hamilton circuits and also has Hamilton paths. You would just go A, B, E, C, D, A, or so on. Lots of different ones you could do. But just because a graph has no Euler circuits or Euler paths does not mean that it has no Hamilton circuits and paths. So you can see a lot of differences between the two already. All right, so looking at this graph, this one's kind of interesting. It does in fact have Euler circuits. You could go from A to B to E to C to D to E to A, and back where you started going through each of them. But it does not have any Hamilton circuits, because what's going to happen is from A to B to E to C to D, we've already used E once, so we can't go from D back to E and up to A, and there is no path or edge going from D up to A. In fact, no matter where you start, because E, you have to go through it more than once, there is no Hamilton circuits. However, there is a Hamilton path, and that's what I just gave to you, was A to B to E to C to D, because you're starting at A, ending at D, and you've gone through each of the vertices just once. All right, so again, some more for you to take a look at. I'm not going to go through all of these with you, but it does give you a nice summary down here about which ones of those examples had Euler circuits, which ones had paths, and also which ones had Hamilton circuits and which ones had Hamilton paths. So it might be a good idea to go through and try to find both the Euler circuits and paths and the Hamilton circuits and paths for each of the respective graphs in order to kind of make sure it makes sense. Now, obviously, there are some similarities between Euler and Hamilton in that they both are describing paths and circuits, but there's a lot less in common than you might think. Really, as far as everything goes, there is no Hamilton circuit or path theorems in the same way that we had Euler paths and Euler circuits. And we had the theorems that Euler developed to help with those, which is kind of unfortunate because we had some really nice theorems that were really useful in helping us to decide if an Euler path or an Euler circuit was possible. We don't actually have that with Hamilton. With Hamilton paths and Hamilton circuits, there's really no way to just tell by looking at a graph if there is a possible path or circuit. So yeah, this last slide just kind of summarizes that up. Surprisingly, there are no such theorems. Determining if your graph has a Hamilton path or circuit can be very easy, but also very hard. It all just depends on the graph. Now, we will actually have some algorithms similar to Fleury's algorithm, which will help us find the Hamilton circuits or paths, but there aren't any theorems that can help us to decide if they're possible or not. So in the next video, we will start to look at some of those algorithms for determining what the different paths or circuits are for Hamilton. Until then, have a great rest of your day.